So we've talked about how to use latches as state elements for building a counter, and we've talked a little bit about how you design an SRAM array. Now let's talk a little bit more in detail about how you actually build SRAM and DRAM. So to get started, what is SRAM? Well, SRAM is static random access memory. And what static means is it keeps its value itself. So each of the memory cells in an SRAM array have power coming to them, and they use that power to hold on to their own value. So inside an SRAM cell, what we have is we have two inverters and a feedback loop. So one inverter, it's fed back into another inverter and feeds back to itself. And here's the output from that. So how does this work? Well, if we have 0 going into the first inverter, it's going to invert it to 1, and then we have 1 going into the second inverter, and it's going to invert it back to 0, and so it's going to keep the value in there. It's feeding back on itself. So the output here is 1, and it holds the value as long as the power is turned on. And why does it hold the value? Because each of those inverters use the power to keep converting their inputs of 0 to an output of 1, and so they reinforce the value. So remember, what this is this feedback loop. It sends the data around and around and holds on to the value. So how do we write into one of these memory cells? Well, here's a look at one of the memory cells, and we have a new device on it. We put a pass gate on it. And a pass gate is a transistor that just allows you to write a value into it. So when the input to this pass gate is 1, it'll allow an input to go into the inverters. So I've got 1 in my input. I set my pass gate to 1 to enable me to write into it. And now that 1 goes into the loop, and it propagates around to the loop and updates the value. So now the output becomes a 0 because it's outputting the invert. So the other way to think about this is when the pass gate is enabled, I can write into this feedback loop, and what I wrote in now goes around and around in the feedback loop. So if you look at this, what's the difference between the input and the output? Well, there really isn't a difference. In fact, if you are to write, you can write in through the output on an SRAM array as well. You have to be careful how strong your inputs and outputs are to make sure you don't overwrite them, and that's one of the reasons it's tricky designing memories. So now can we take this SRAM array cell and build a latch out of it? So the first latch we're going to build is a transparent latch. And so what a transparent latch is when the clock is high, the input goes straight through to the output, and when the clock is low, the last value is latched or held, and the input is ignored. So here's my little back-to-back inverter doing its feedback loop, and what I'm going to do is put a switch on here. Usually it's a pass gate, just like we saw before. And I'm going to control this switch with the clock. So what that means is when the clock is 0 and the switch is open, the input is ignored. So whatever value was last going around in my inverters is the output. It stays the same, or it's latched. When I, however, have the clock be 1 and that switch get closed, the value that's in there is still output, but if a new value comes in, it's going to replace that and go directly to the output. So this is a transparent latch. When the clock is high, the value goes straight through, and when the clock is low, the value gets stored. But there's a problem with this. Because the output changes when the input, you can have feedback loops. So for the whole time that your clock is high, you can have feedback loops going through your combinational logic this way. So how do we avoid this? Well, we create what's known as an edge-triggered, or a D flip-flop. And this is something that only updates the output when the clock transitions from 0 to 1. That is, when the clock edge rises from 0 to 1, then we change the output. This is also known as a master-slave latch, because we have two latches put together, and we'll see how that works now. So to build a D flip-flop, or a master-slave latch, we put two of those transparent latches together, and we hook them up slightly differently. So the second one is going to be hooked up to clock, and the first one's going to be hooked up to not clock. And so what this means is we're going to load data into the first latch and the second latch differently. And by doing it differently, we'll only update the output when the clock changes from low to high. Let's take a look at that. So say we start off with both of our latches having 0, and they're both outputting 0. Our input is 0 in this case, and let's say our clock is 0. So if the clock is 0, the first latch is closed, and we go right into the first latch. So we can write that 0 in. But the second one is open, because clock is 0, so we don't have that second gate closed. So we can't transfer data from the first latch to the second latch. Now if we change the input to 1, well, the clock is still 0, So that's going to go into the first latch and it's going to update its value to 1, but it's not going to go to the second latch. So the second latch's output is still going to be 0. So the input does not change the output because the clock is low. Now look what happens when the clock goes from low to high. So the clock was low before and now it's going up to high. What happens here, our input's still 1, but now we no longer store data into the first latch because our clock is now high. But we still have that new 1 value stored into the first latch. And now what we see is that the second latch is closed, so we can store the data into it. So now the 1 from the first latch gets transferred to the second latch and goes to the output. So what we saw here is that the output does change when the clock goes from 0 to 1. The data is transferred from the first latch to the second latch. Now if we follow this with the clock still being 1 and we change our input, well, nothing happens because the first latch doesn't have its gate closed, so the input can't go into the first latch. It will stay 1 and we'll still have 1 as our output. So the input does not change because the clock did not change from 0 to 1. So what do we have here? Well, the data moves to the first latch when the clock is 0. This is just like a transparent latch, but the data doesn't get out because it's only going to the second latch. But data only moves to the second latch when the clock is 1. And so this allows us to only send data from the input to the output when the clock edge is rising. And this is the way most logic is designed. In fact, this is what we saw when we looked at the counter example, and this is the most common state element used in pipelines and the like. So another look at these edge-triggered flip-flops. So when the clock is 0, the value is latched into the first latch. And then when the clock is 1, the value is now transferred from the first latch to the second latch in the output. And that means the input's ignored because the first latch is open. And that's how this edge-triggered latches work.